Bioinformatics Micromodules, demonstration of the occurrence algorithm. In this module, we use a complete example to demonstrate how the occurrence algorithm constructs a suffix tree and explain why it takes linear time. First, let's have a quick recap of the whole algorithm. At the beginning, we set the starting node to the root and the number of leaf nodes to 0. Then we have n iterations, where the ith iteration is for inserting information about the ith position of the sequence into the suffix tree. In each iteration, we know that the first insertions must all be type B cases, which can be skipped, and therefore we start with the first non-type B insertion according to the previous number of leaf nodes. For that insertion, we first need to search for the insertion point by traversing down the tree from the starting node. If the new character triggers the creation of a new node, meaning that it is of type A, we create a node and increment the leaf count. We also find the starting node of the next insertion using suffix links based on the rules we described in the last module. If a new internal node was created in the last insertion of this iteration, we create a suffix link for it. Finally, if the insertion did not trigger the creation of a new leaf node, meaning that it was a type C insertion, we end the current iteration and start the next one. Let's see how this algorithm works using our example reference sequence as $. At the beginning, the tree is just a root node with a suffix link pointing to itself. The starting node, which will always be highlighted in red throughout this whole demonstration, is of course the root node at this moment. The first iteration contains only one insertion, which is the insertion of the character at position 1 of S, a T. We find that the current node does not have a child with a label starting with T, and therefore this is a type A insertion, which means we create a new leaf node. Notice that the ending position of the node label is written as I, since at the ith iteration, it will always take the value of I directly without the need for an explicit update. According to our rules, since this is a type A insertion, we follow the suffix link of the current node and reach the root node itself, which will be the starting node for the next insertion. Now we start iteration 2. Since at the end of iteration 1, the tree had one leaf node, we can skip the first insertion of this iteration and directly work on the second one. This insertion is about the suffix A, highlighted in red. Again, since the current node does not have a child with a label starting with A, we create it using type A insertion, and the current node will again go back to the root. Next, we start iteration 3, and we skip the first two insertions since they are all of type B. For the third insertion, which is about the suffix T, we find that the current node already has a child with a label starting with T. Therefore, this is a type C insertion, and we end this iteration directly. Then in iteration 4, we skip the first two insertions. The third insertion is about the suffix TA. The current node already has a child with a label starting with T, and the second character of it is also A. Therefore, it is a type C insertion, and we can end the iteration directly. Now we start iteration 5, and we skip the first two insertions. The third insertion is about the suffix TAC. The current node already has a child with label starting with T. We do not need to check whether the second character of the node label is A, since it must be the case given that its length is longer than 2. We do need to check whether its third character is C and find that it is not. Therefore, we need to create a new leaf node for C, connect it to a new internal node that represents TA, and the remaining of the original node label is moved to another child. Notice that in an actual implementation, all these are done by manipulating the starting and ending positions of node labels, but not the actual characters in the labels. Since a new leaf node is created, this insertion is of type A, and therefore, according to our rules, we should update the starting node. Since the current node, which is the internal node, does not have an outgoing suffix link, we go to its parent and follow its suffix link instead to reach the root node itself as the next starting node. Then we work on the next suffix, AC. There is already a child of the current node with a label starting with A, but the second character of that label is not C, and therefore we also need to create new nodes as in the previous insertion. Also, since an internal node was created in the previous insertion, we should link that internal node to this new one. Finally, following the rules, we will update the starting node to the root as explained before. The last insertion of this iteration is about the suffix C. Since the current node does not have a child with a label starting with C, we create a new leaf node as a child of it. We also add the suffix link and update the starting node to the root according to the rules. Iteration 6 is quite simple. Since we had 5 leaf nodes at the end of iteration 5, we skip the first 5 insertions of this iteration. The last insertion is about the suffix A, and there is already a child of the current node with a label starting with A, so this is a type C insertion, and we end the iteration directly. In iteration 7, the first 5 insertions are skipped. The 6th insertion is a type C case, and therefore the iteration is ended without having any modification to the tree. In iteration 8, again the first 5 insertions are skipped. For the 6th insertion, we find that the current node has a child with a label starting with A, and the total length of this label is 1. So we move to this node and look for the remaining of the suffix TT. The current node has a child with a label starting with T, but the second character of that label is A instead of T, and therefore we need to create new nodes as before. Following the rules, since the current node does not have an outgoing suffix link, we go to its parent and follow its suffix link to reach the root as the new current node. Now for this suffix TT, after the downward search, we find that new nodes also need to be created, and so we create them. Also, a suffix link is added pointing from the previous internal node to this new one. Then following the rule, the current node is updated to the root. Finally, the last suffix of this iteration, T, is a type C case. After adding the suffix link, we end this iteration directly. In iteration 9, the first 7 insertions are skipped. After downward search from the current node, we find that it is a type C insertion, and therefore we end this iteration directly. In iteration 10, the first 7 insertions are skipped. The 8th suffix TAG requires a new leaf node, and so we create it. Notice that in this case, it is not necessary to create a new internal node. This pre-existing internal node has an outgoing suffix link, and therefore we follow it to reach the new starting node, which is the node now highlighted in red. The next suffix to handle is ag. And again, we need to create a new leaf node. So we create it. Then following the suffix link, we reach the root as the new starting node. The suffix that we need to handle now is g, and we create a new node for it as a child of the current node. Following the outgoing suffix link of the current node, the new starting node is again the root. Finally, in the last iteration, we skip the first 10 insertions. The 11th insertion is about the suffix $, which leads to the creation of a new child of the current node. The whole suffix tree has now been created. Let's analyze the time complexity of the whole algorithm. First, let's see how many times each type of insertions has happened. For type A, since each of them creates a new leaf node, and finally there are n leaf nodes, the total number of type A insertions across all the iterations is exactly n. For type B, since they are all skipped, the number of them is not important. For type C, in each iteration, we need to perform computations only for the first one, and therefore there are at most n of them in total across all iterations that had computational cost. Next, let's talk about the searching time needed to determine the type of each insertion. For type B, since they can be determined based on the number of leaf nodes from the last iteration without doing any tree traversal, they have no computational cost. The most interesting part of this complexity analysis is the case for type A and type C. It is actually not easy to analyze how many nodes we need to visit when searching down a tree each time. Instead, we will consider all the type A and type C cases together. This technique is called an amortized analysis. Every time after a type A insertion, we need to update the starting node. If the current node does not have a suffix link, we first need to go to its parent, which reduces the depth by 1. Then we follow the suffix link, which reduces the depth by at most 1, as explained in the last module. Therefore, each time when we update the starting node, we reduce the node depth by at most 2. For a total of no more than 2n type A and type C insertions in total, we decrease the depth of the starting node by at most 4n in total across all iterations. On the other hand, we know that in the final tree, the maximum depth is at most n, which only happens when every character of the longest suffix occupies a separate node. We also know that if we are traversing down the tree, we cannot go beyond a leaf node. Therefore, starting from the root node, which has a depth of 0, with a total reduction of the node depth by at most 4n, the total increment of the node depth during the downward traversals can be at most 5n. To conclude, the number of moves from a node to another throughout the whole process is order n, each requiring only a constant amount of computations. Finally, after determining the insertion type, for a type A insertion, we need to create 1 or 2 nodes, which requires constant time each. For a type B insertion, the only cost is updating the value of I, which requires constant time for each iteration and thus a total of order n time across all n iterations. As for type C, they do not require any operations. For type A and type C, sometimes we also need to create a suffix link, which only requires constant time. Considering all these together, the overall time complexity of the whole algorithm is order n for a sequence of length n.